Alright, so let's now look at the calculation, the kind of calculation we just did with the nitrogen 2 oxide and nitrogen 4 oxide, just to see how you can be able to do that practically. In case you are given a table, that's obtainable. You can be given a table and you'll be asked to tell what is the order of reaction. So let me show you how you can be able to do that, and then you can go back and solve for the nitrogen 2 oxide and nitrogen 4 oxide, which I just told you how to be able to do that, and then see that you are a master at it. So what we have here is ethanol. Ethanol is, old name is acetaldehyde. So this is ethanol. Ethanol decomposes. Ethanol decomposes to give methane and then carbon 2 oxide. So ethanol decomposes to give methane and carbon 2 oxide. So the initial rate of decomposition of acetaldehyde, which is also known as ethanol, was measured at a series of different concentrations with the following results. So the concentration of the acetaldehyde as ethanol in mole per liter. Remember, I already told you that 1 liter, I've told you 1 liter is equal to 1 dm cube. So in mole per liter, we send as mole per dm cube. And the rate, this is rate is mole per liter per second. So remember we said rate is concentration per time. So if concentration is mole per liter times 1 over, let's assume that time is in seconds. Are we together now? So that's going to be mole times 1 will give us mole over liter times seconds will give us liter seconds. So it's something as mole per liter seconds, which is something as mole per liter per seconds. I hope that's making sense to you now. So that's basically what we have here. So mole per liter times 1 over s. 1 over s is like per seconds. So that's mole per liter seconds. Something as mole per liter per seconds. Which something as mole per liter per seconds. So that's basically it. For you to understand how this one functions, it's very simple. It's just for you to write this something now is mole over liter times 1 over s in indices is s raised to the power of minus 1. It's small letter s, okay, is the L that is capital letter. S raised to the power of minus 1. So what you now simply have is mole per liter per seconds. Simple stuff. Alright, so that's basically what we have for the units. I just had to do that so I can understand how to be able to work with units and not make mistakes when you are writing your examination. So the question is, what is the order of reaction? What is the order of reaction? So for you to be able to get what the order of reaction is, you need to take note of the concentration of the reactants in question. Now, when we work with nitrogen 2 oxide and nitrogen 4 oxygen and then producing nitrogen 4 oxide, I tell you that if you are having more than one reactant, the one other reactant has to be constant so that you can be seeing the change in the rate of reaction with respect to the reactant under review at that particular point. So I showed you how that when oxygen is constant, then you have a doubling of nitrogen 2 oxide to give a quadrupling of the rate of reaction. And then when nitrogen 2 oxide is constant and you have a doubling of oxygen, you have a doubling of the rate of reaction. So in this particular context, you don't need to keep another thing constant because the only reactant is acetaldehyde as ethanol. So every other thing is already like constant on its own without having to make anything to become constant basically. So how do you now solve for the order of reaction? It's very simple stuff. We know that for this particular compound, the rate is equal to K brackets CH3 CHO raised to the power of, we can decide to use x. Now that's something I need to let you know. We can use x, you can use y, you can use m, you can use n. Some textbooks you find m and n, some textbooks you find x and y. Whatever letter you want to use, you can use that. For us in this particular case, let us use m. For example, let's use m. So m represents the order of reaction. Since we have only one reactant here, it means that the order of reaction with regards to this reactant is still going to be the overall order of reaction because this is what is responsible for affecting the rate. So the order of reaction is our m. So we know that for this particular equation, rate is equal to k, this is equal to m, and we know that m is not necessarily like the coefficient like I've mentioned before. It is determined from experiments. And we say that when you have been given concentration and you have been given rate, you can determine the order of reaction. That's why this question has been put forth. What is the order of reaction. Now, for us to be able to explain, get this done, it is very simple. We have different rates at different times, and we have different concentration at the different rates. So we can actually have something like rates 1, for example, is equal to K. Remember that K is not dependent on concentration, so K is constant. Is equal to K, then concentration of this guy, concentration 1 of this guy raised to the power of M. We can have rate 2 equal to K, concentration of this guy, 2 raised to the power of M. Are we together now? You can have rate 3 equal to K, then you have CH3 CHO 3 raised to the power of M. You can have rate 4 and so on and so forth. That simply tells you that for every one of them, the K is constant. So for us to be able to now get our M, we can simply do something very simple, which is normal stuff we do in maths. So we can say, let us work with two equations, and we can call this one equation 1, and we can call this one equation 2. So let us work with two equations, because what we want to do now is to eliminate the K. If we eliminate K, we already know what rate is. Are we together now? So this is rate 1, rate 2, rate 3, rate 4. This is concentration 1, concentration 2, concentration 4. The only thing we don't know is K. For us to be able to eliminate K, we will do what is called dividing equation 2 by equation 1. So if we call this thing equation 2 and call this equation 1, we will need to now divide equation 2 by equation 1. If we divide equation 2 by equation 1, we are going to have, just for the purpose of space, we are going to have rate 2 divided by rate 1. What is rate 2? Rate 2 is 0.34. 0.34. What is rate 1? Rate 1 is 0.085. 0.085 equal to K divided by K is going to give us 0. So it's going to give us 1. K divided by K is going to give us 1. So K is out of the game. So we now have concentration 2 divided by concentration 1. We now have concentration 2 divided by concentration 1. So that's going to give us concentration 2 is 0.2 and concentration 1 is 0.1. And then this is raised to the power of M, and this is raised to the power of M, and according to indices, you already know that this can actually be put as 0.2 divided by 0.1, all raised to the power of M on the basis of indices. Are you following me now? So by reason of doing division of 2 by 1, we have eliminated K, because K divided by K is going to give us 1. Now we have gotten this. The next thing is to get values for this, and the next thing is to get values for this. So using a functional calculator, 0.34 divided by 0.085 is going to give us 4. 4 equal to 0.2 divided by 0.1 is going to give us 2 raised to the power of n. The next thing for us now is to now convert this to indices in such a way that what we have as the Bessel number is 2, and then we can now find our n. If 4 is equal to 2m, 4 is the same thing as 2 raised to the power of 2, which is equal to 2 raised to the power of m. So 2 raised to the power of 2 is 4, and by implication that's 2 raised to the power of m is that. The implication now simply means that m is equal to 2. So if m is equal to 2, what does that tell you? It simply means that the order of reaction is a second order of reaction. And what does that simply mean? It simply means that for every doubling of concentration, there's a quadrupling of the rate of reaction. So we have already seen what I mean by the quadruple. 0.34 divided by 0.084 gave us 4. Meanwhile, the concentration 0.2 divided by 0.1 gave us 2, showing that for every doubling of the concentration, there's a quadrupling of the rate of reaction. You can choose that you don't want to work with rate 2 and rate 1. You want to work with rate 3 and rate 4. It is the same thing, because the order of reaction is the order of reaction, irrespective of which of the rate and which of the concentration you are working with. So we can also do similar stuff. Somebody else can choose, I don't want to do rate 2 and rate 1, I want to do rate 3 and rate 4. So you can simply do rates, equation 4 divided by equation 3. Like, do you understand what I'm trying to say about that? Instead of having rate 1 and rate 2, you're not doing rate 4. K concentration 4 raised to the power of m, rate 3, K concentration 3 raised to the power of m. When you do the division for rate 4 will be 1.35, 1.35, rate 3 will be 0.76 equal to, why this guy is 0.40 divided by 0.30, 0.40 divided by 0.30, and all of these things are raised to the power of m. All of these things are raised to the power of m. So when you get to do that, it is going to give you 1.35 divided by 0.76 divided by 0.76 to give you 1.776 equal to, then 0.4 divided by 0.3 is going to give you 1.333 raised to the power of n. The next thing is for you to now find a common denominator that when you raise to the power of n, you can able to do that. For you to be able to do that, the next thing you need to do is, for this particular answer you have 1.333, you can do raised to the power of 2 so you can see what it will give to you. If you do raised to the power of 2 with your calculator, it will give you 1.776, simply telling you that 1.333 raised to the power of 2 is equal to, raised to the power of 2 is equal to 1.333 raised to the power of m. Therefore, m is equal to 2. So whether you are working with rate 1 and 2, rate 1 and 3, rates 3 and 4, whatever you are working with, you can, somebody else can even choose to work with rate 2 and rate 4, rate 1 and rate 3. Whatever you choose to work with, it will still give you the same answer. So these are things that you can practice and learn how to be able to calculate order of reaction, having been given the concentration of this and the rate of this. So you can go back to the previous video and try applying these things in line with what I've explained in the previous video and see how that the rate of reaction for the reaction between nitrogen 2 oxide and oxygen is rate equal to, so you can confirm that the rate is now equal to K NO raised to the power of 2 and then O2 raised to the power of 1. So you can go back and then do that particular stuff. So let's now come over to order of reaction. So the question is, what is order of a reaction? Order of reaction or order of a reaction refers to the power to which the concentration of a reactant is raised in the rate equation of the chemical reaction. So order of reaction refers to the power to which the concentration of a reactant is raised in the rate equation of the chemical reaction. That's very simple. So this is the rate equation, and then the power to which the concentration of the reactant is raised, what is referred to as the order of reaction. So the reason why we say the order of reaction for this guy is 2, because we have discovered that m is equal to 2, and if this is equal to 2, automatically this is the second order reaction. Very simple stuff. All right, so it indicates, that is that it indicates how sensitive the rate is to changes in concentration of each reactant. So it indicates how sensitive the rate is to changes in concentration of each reactant, because in a zero order reaction, the rate is independent of the concentration. In the first order reaction, the rate is directly proportional to the concentration, making it such that if you double the rate, if you double the concentration, you automatically double the rate. Meanwhile, in the second order reaction, the rate is much more higher than the concentration, such that if you double the concentration, the rate quadruples. So it's a matter of sensitivity that is being shown by the order of reaction. So with higher values being more sensitive to the concentration, change in concentration of the reactant. So it can be a zero order reaction. So order of reaction can be 0. It can be fraction. I have talked about that. It can be a whole number, and it can even be negative. Rate of reaction can also be negative. In case you see your examination and you find negative values, those are also obtainable when we talk about the rate of reaction. So rate is equal to K bracket A, that's concentration of A raised to the power of S, concentration of B raised to the power of Y. I told you before that in some other textbook you may find M and N. It's optional. All that we just need to know is that whatever it is raised to the power of represent the order of reaction. And what is the overall order of reaction? I said that the overall order of reaction is X plus Y is equal to the overall order of reaction. We can call that N for the purpose of just clarity. So if X plus Y is equal to N, N is the overall order of reaction. So that's about that. So if you make K subject to a formula, K is now equal to rate divided by this concentration raised to the power of their different units. And where concentration of A is equal to the concentration of B, we now have that K is equal to, what is rate? Rate is concentration over time. Change in concentration over time. I talked about that. Times 1 over, if these guys are the same, it simply means that we can simply do x plus y, which are given as n. Automatically, it's 1 over concentration raised to the power of n. So what are the units of rate constant? So if we take, I want to believe that you understand exactly what I explained here. Rates over this guy. Now let me just break it down. So rates, this is rates divided by a raised to the power of x, b raised to the power of y. That's what we have there. And we said that if a is equal to b, it simply means that this particular expression can also be written if a is equal to b. You now have this raised to the power of x plus this raised to the power of y. Times this is the power of y. In indices, what you simply do is that since they are the same, you simply add this up. So you now have that our a is equal to x plus y. I've already said that x plus y, we are denoting it by n. So it simply means that a is now equal to, that's now a raised to the power of n. So this a raised to the power of n is also now represented as concentration. It's what we now refer to as concentration. And just for the purpose of clarity, let me now go further and also talk about this. So what we have here now is rates divided by concentration raised to the power of n. I've shown you how we got concentration raised to the power of n. And then that is something as, what is rate? We already know that rate is change in concentration over time. Change in concentration over time. And when you have divide, to convert it to multiplication, you do a reciprocal of this. That's now 1 over concentration raised to the power of n. So that's basically how we arrived at concentration over time times 1 over concentration raised to the power of n. And why is this particular stuff important to us? Because the next thing we want to talk about is the units of, we want to talk about the units of rate constant. And that's, for us to get that, let us assume that we are working with concentration, unit of concentration being mole per dm cube. Remember that mole per dm cube is same thing as mole per liter. I've mentioned that several times in this video. So whether you see mole per dm cube, mole per liter, they are the same thing. Then let's assume that our unit of time we're working with is seconds. So if we're working with that, what are now the units of the rate constant? So zero order reaction is now concentration mole per dm cube divided by time S times 1 over concentration raised to the power of 0. According to indices, anything raised to the power of 0 is equal to 1. So this guy raised to the power of 0 is equal to 1. 1 divided by 1 will give us 1. Automatically, the unit of rate constant, which is our K, the unit of rate constant in a zero order reaction is now equal to, and why do we use n as 0? Because n is the overall order of reaction. And if the overall order of reaction is 0, it simply means that it's a zero order reaction. So our rate constant is now equal to mole per dm cube per second. So mole per dm cube per second. So zero order reaction is concentration per time. Concentration per time. Then for first order reaction, you now have, instead of having 0, now you're now having 1. If you have 1, this will cancel this. So you now have 1 over s. And so for first order reaction, you have per seconds, which is actually like per time. I hope that's making sense to you. That is per time. While for second order reaction, we have concentration over s times 1 over concentration raised to the power of 2. So only 1 will be cancelling out. If you cancel 1 out, automatically what is now going to be left is now going to be mole minus 1 dm cube s raised to the power of minus 1. So because the dm cube is now coming to the top, that's why it's called dm cube. And then the mole that is ordinary is now mole per mole dm cube minus 1. So for this first order reaction and zero order reaction, first order reaction and second order reaction, for zero order, it is concentration per time. While for first order, it is per time, and for second order, it is per concentration per time. Now, why is the unit of rate constant important to us? The unit for rate constant is important to us simply because from the unit of the rate constant, you can be able to tell what the order of reaction is. So because a question can be given to you, we'll see examples of those things. A question can be given to you about a particular reaction, and they will not tell you the order of reaction, and you are expected to know the order of reaction for you to be able to solve the question. So the way you will know the order of reaction is simply by looking at the unit of the rate constant. So if the unit of the rate constant given to you is just concentration per time, for example, mole per dmq per seconds, it simply tells you that this particular reaction is a zero order reaction. If the unit of rate constant given to you is per time, for example, seconds per seconds, it simply tells you that it's a first order reaction. And if the unit of the rate constant is per concentration per time, which is an example, per mole dmq per second, it simply tells you that it's a second order reaction. And that is the necessity of having all of these things in your head, because it will play a useful role in the event that you're not to the order of reaction and you're expected to know it. The way to know it is to know the unit of rate constant for the different order of reaction. So the overall rate of the reaction is controlled by the slowest step in the reaction. The overall rate of the reaction is controlled by the slowest step in the reaction, and that step is called the rate determining step, because the reality is that if that particular step do not make progress, nothing happens. So, and the speed at which that particular step makes progress is what determines the overall rate of the reaction. So we're now going to go into details and start talking about the different rates of reactions or order of reactions that are important to us in pharmacy school.